Well, let's talk about the application of reinforcement learning for information retrieval. Um, First, we'd like to talk about the usage of DQN that we have just tried. To make use of reinforcement learning for a real-world problem like information retrieval, it's similar to solving problems like putting an elephant into a fridge. You only need 3 steps. Open the fridge, put the elephant in, and close the door. So similarly, if we want to solve a problem like recommendation using reinforcement learning, we only need to carry out the 3 steps. First, we need to formulate the problem as a market decision process. So this basically means that you need to think what the environment is, what the agent is, and the states, the actions, and the rewards. Then choose a reinforcement learning algorithm, such as DQN. Third, run the reinforcement learning algorithm. And that's it. So DQN has been used for recommender systems. First, because it's recommender systems is kind of like a computer game, right? So the system would recommend a list of items to the user. The user would may like the item recommended by clicking on it or purchasing it. And then this feedback would be made use by the recommender system to optimize the recommendation algorithm. So next time it would try to make better recommendations, and hopefully in the long run we could the user would be happy with the recommendations more and more. So recommender systems has been an important application of information retrieval because it helps to mitigate the information overload. And this is a problem which can be solved by reinforcement learning. But before that, we have seen many techniques for recommender systems from user-based capital filtering, item-based capital filtering, and then there are more advanced techniques such as factorization machines. But all these existing recommender systems, they view the recommendation process as a static process. Usually they follow some greedy strategy to just try to maximize the immediate reward from users. For example, try to make recommendations so that the users would click on that recommendation. So one particular objective is to maximize the click-through rate in recommender systems. And this is just the immediate short-term reward. So if we want to go beyond that to maximize the long-term reward for users and also continuously update the recommendation strategies to address the dynamic changes of users' interest, it would be beneficial to make use of reinforcement learning. So here, the users would interact with the recommender system continuously. And so imagine that you are going to move to a new house and buy the new bed. So it makes sense to think about recommending a number of items to the users, not just the bed, but also the user is likely to need the bed sheet, the pillows, the duvets, and so on and so forth. So it makes sense to consider the long-term effectiveness of the recommendations. So we are going to look at a few papers in recent conferences. The first one comes from the Pennsylvania State University and Microsoft Research Asia. And this is one of the early papers making use of DQN for recommender systems. In this case, particularly for news recommendation. And so what the objective of their work is to optimize the long-term effect in recommendation. So here's an example scenario. So when a user requests for news, the recommendation agent would forecast what news item he would like to see. And so there could be multiple news items. For example, one about Kobe Bryant, and the other is about a thunderstorm. Maybe at the current round, they have equal opportunity to be liked by the user. But what about the next round? So if a news item about Kobe Bryant has been recommended and the user has found it relevant, it's more likely that he or she would want to read more news articles about basketball. But for the summer storm, maybe that's just the end of the recommendation. So if we think about the long term, then we could find better strategies by using reinforcement learning. So particularly, the news recommendation is very dynamic. It is reported that the life period of for news is usually very short. So the average time from the news article being published to the news article being clicked last time is just roughly 4 hours. And the user's interest may change during time. So this graph shows the categorization of the news that one user has read in the last 10 weeks. During the first few weeks, the user prefers to read about politics, which is represented as the green bar. And but his interest gradually moves to entertainment and technology over time. So the other issue is that there could be useful signals in addition to simply the click or skip actions from the users. For example, whether the user would return to this news website would be also a very good indication whether the user has been happy with the recommendations or not. So the user's clicks on news are usually very dense in a short period. And then some users would return back, for example, after 1 day or 2 days. But some users would just leave the site permanently. So how soon the user will return back to the news recommendation service will indicate whether he's satisfied with the service or not. And one advantage of using reinforcement learning is to incorporate such additional signals So it is a lot more flexible than simply making use of supervised learning, for example. Because you could incorporate these signals into the reward function. So we have seen that you could, for example, do something to manipulate the reward function to push the system towards the direction which would be beneficial to the users. And third, right, the user may get bored if the recommender system keeps recommending the same kind of news items. For example, if the user has seen the news report about Kobe Bryant, he or she might be interested in basketball, but if we only recommend news items from about NBA, then it may be not desirable. So these are some of the motivations for people to look into the usage of deep reinforcement learning. So to address the dynamic nature of news recommendation, the online learning feature of deep reinforcement learning would be helpful because the agent is constantly updating the policy. And we could also consider some other performance measures for the long-term effect. Here, we could think about the design of the reward function and in particular, some of these reward functions may not be need to be differentiable. So you could have a very complicated reward function, and also we have seen that the reward shaping would help the learning. And last but not the least, the diversity of the recommendation could be addressed by deep reinforcement learning in a principled way, because the trade-off between exploitation and exploration is built in for reinforcement learning algorithms. So to formulate the problem of news recommendation as a market decision process, we consider the environment and the agent. So the environment consists of the pool of users and also the pool of news items available for us to recommend. The agent is just the recommendation algorithm. The state would be the feature representations for users, and the actions are just the news items for us to choose as the items to be recommended for users. So we need to have these feature representations for news items, and for example, use softmax function to determine which news items we should pick as the recommendation. And the reward would be the user's feedback. So this would this would include the standard click or skip labels, whether the user has clicked on the news article to read it or not. This is just the binary signal that has been used by all the existing news recommendation algorithms. But we could also incorporate other signals like the estimation of users' activeness. Right. So each time when a user requests a news, then the state representation, which is the feature of news of users, and a set of the action representations. In other words, the news candidates, they would be passed to the agent, which is the reinforcement learning based recommendation algorithm. And then the agent will select the best action from the available news items. So the a list of the news items would be sent to the users, and then the recommendation algorithm would fetch the user's feedback as the signal for training. So all these recommendation and feedback logs would be stored in the memory of the agent for the episode replay, as we have seen in the DQN algorithm. So every 1 hour, the agent will use the log in the memory to update its recommendation algorithm. So the framework of the model looks like this. It has two parts, the offline part and the online part. So in the offline stage, the recommendation algorithm would make use of 4 kinds of features. Features representing the user, the news item, also the context, and the interaction between the user and the news item. So these 4 kinds of features would be extracted from the news and the users and the context. Then a multi-layer DQN will be used to predict the reward from these feature representations. And then the best news items could be selected by the DQN. So this network is going to be trained using the offline user news click records in the log. So during the online part, the recommendation agent will interact with the user and update the network by following this sequence of activities. So once the news item is selected, it will be pushed to the user, and the user would decide whether to click it or not. So this feedback would then be used to update the DQN policy. So each time, at each time step when the recommendation has been carried out, the system would perform a minor update to the DQN policy, and then after a certain period of time, like 1 hour, the DQN would have a major update using all the logs in the memory. So the interesting part in the DQN network architecture is that they do make use of this so-called dueling network architecture that has been mentioned by Miguel. So it seems to be beneficial to separate the estimation of the Q function, the Q value, into 2 parts. One is the value, which only depends on the state, and the other is the so-called advantage, which depends on not just the state but also the action. So intuitively, it'd be better if you, when we estimate the value function, we only use the relevant features such as the user and the context, but not those which are for the particular action only. So you could have you could aggregate all the data about that particular state and focus on estimating the value of the state. And this has been shown to be useful in practice. And they, as I've mentioned, they used the user activeness, how soon the user would return back to the news recommendation service as an additional reward So this is done by survival analysis, which is a very different topic. And but the point is that you could make use of many different types of useful signals in the reward function. And they also perform the exploration, slightly differently from the standard, random exploration strategy. For example, people often use just epsilon greedy exploration, which randomly choose the actions with a small probability. But here it's not desirable because when you make recommendations, you don't want to make things which are just random. That would severely harm the user's experience. So what they do is that they use so-called explorer network, which is similar to the current DQN network, and they try to make small perturbations to that network so that it would recommend a news item which is in the small neighborhood of the current recommendation. So it is exploration, but not completely random. And then you could use the slightly randomized recommendation within the neighborhood to interpolate it with the to interleave it with the original recommendation list. Then the combined list would be provided to the user so that you could have the trade-off between exploitation using the DQN network that has been well trained, and also the slightly different DQN network which can help you to explore the unseen space. So this is for the news recommendation, which is one of the early papers about using DQN for recommendation. And so next, let's have a look at the application of DQN in recommending recommender systems for e-business. So this is a paper from researchers working for JD.com, which is a Chinese Amazon. And so the key point is that in recommender systems, we want to make use of both of the positive feedbacks where users click or purchase the recommended item. But also we want to make use of the negative feedbacks. If the user skip some of the recommended items, it may indicate that the user may not like those recommended items. So next time they should be taken into account by the recommender system to avoid those kind of recommendations. So what they suggest is that we should have two separate paths, one for the positive feedback and one for the negative feedback. And because you could have a list of positive feedbacks and a list of negative feedbacks with different lengths. So they use the recurrent neural network, one type of recurrent neural network called GRU, which is a simplified version of STM, to encode that sequence of positive or negative feedbacks into one feature representation of the as the state. So the motivation is that when we do the recommendation, we want to recommend an item which is similar to the clicked items, the positive feedback, and dissimilar to the skipped items. So following that intuition, we divided the DQN into two parts. And so with part of the state capturing the positive feedback and the partial state capturing the negative feedback. Furthermore, they got the inspirations from pairwise learning in information retrieval. So to recommend the items belong to the same category, the users sometimes click on the recommended items and sometimes skip on the recommended items in the same category. For example, here in the category B, the item A2 was clicked by the user, but the item A5 was skipped. So this provides very stable and useful signals for us to rank these two items according to the user's preference. And this is helpful because in recommended systems similar to search engines, we care a lot more about the relative order of the items rather than the absolute score of the items. So it is found that you could add these pairwise regularization term to maximize the difference of the Q values between the clicked items and the skipped items. So because DQN in the end is to optimize the reward accumulated along with time through the gradient descent. So it is convenient for us to add this pairwise regularization term to the objective function. And then this would help us to train the DQN so that the difference between the positive items Q values would be very different from the from those for the negative items Q values. Okay, the third paper that I would like to mention is a paper that talks about the joint learning of recommendation and advertising. So this paper is from the work done by researchers in ByteDance. In Western countries, people are more familiar with their mobile app called TikTok. So ByteDance is the company who makes the mobile app TikTok and many others very popular in China. So in recommender systems, we want to maximize the long-term user engagement, and the challenge is to the combinatorial action space. And we often want to perform computational advertising at the same time. So the goal is to is different from the recommender system, because we would like to maximize the advertising value and at the same time minimize the negative influence of the ads of user experience. So this involves several decisions to make. We need to decide whether it is beneficial to interpolate an ad, at which position of the recommended list we should insert the ad, and also which ad is the best for us to insert into the recommendation list. So the target user would browse the mixed list of the recommendations and the ads, and then provide his or her feedback. So here we assume that given a list of the recommended items, we only want to add one ad into the list, and if we think that it is beneficial for the system. And so what they do is to make use of a two-level DQN. The first level is for the recommender system, and the second level is to perform computational advertising. So for the recommender systems, the state would consist of the historical recommended items, the historical ads, and the context. So the action is to come up with a list of the items for recommendation. And so the challenge is that if you want to generate a list directly, there's the problem that the action space will be extremely large because you have this explosion from the combination of all the n items. To address that problem, right, so they use this so-called cascading DQN, which basically means that you want to generate the list by sequentially selecting the items in a cascading manner. So this means that you just choose the recommended items using the DQN one by one until you have a list of all the recommended items. This is a common trick when you need to make a recommendation of a list or a set. You just turn it into a sequential decision problem, which is well addressed by the recommender by the DQN. And then for the advertising, you would need to address these three sub questions simultaneously. So one way to do that is to adapt the DQN network architecture. So instead of just taking the input of the state and action and output the single Q value for that pair of state and action, this DQN would output Q values, one for each location in the list of recommended items list. So assuming that we are recommending K items, then there would be K plus one positions for us to insert the ad. Therefore, they use these K plus one Q values to determine which position to insert the ad. And to determine whether we want to insert the ad or not at all, they also introduce a special Q value output for the position 0. So this one, if this is the highest Q value among all the possible actions, then you would not add the ad to the list of recommendations. So in this way, you could use one DQN to answer these three questions and make the optimal decision. So the DQN for the advertising system would make use of the state, including, so the state would necessarily include the list of the recommendations from the previous DQN for recommendation. So this is a two-level DQN. The first level for recommendation and the second level for advertising. Right. So that's the typical works in recent years for recommender systems using DQN.